In this video, we'll generate the trend line or polynomials of physicist Hermite polynomials using Taylor-Maclaurin SERIESSUM and Linus polynomial regression. We begin with the Hermite polynomials SERIESSUM expansion, which is the summation of a, the coefficient, times 2x raised to the power 2n minus 2k, where the value of n is from 0 to 10. Data validation, list of items, 0 to 10. And the value of k is from 0 to 0.5 n. So this is equal to sequence of 0, 0.5 times n plus 1 column from 0 incremented by 1. So at n equals 10, then k is from 0 to 0.0 to 5. Next, we enter the Taylor-Maclaurin SERIESSUM expansion of the physicist Hermite polynomial. So, RA formula, series sum of this is 2x, so 2 times x raised to the power n incremented by minus 2k, so 2, 0, 2, 4, 6, so minus 2. And the coefficient a will be this range. Here we have the polynomial to the 10th degree and the trend line of the polynomial. Next, we calculate the coefficients starting with the numerator. So RA formula. So factorial n times negative 1 to the power k. So minus 1 to the power k. That's for the numerator. So if this is empty, this should be 0. So this should be 0 because this is empty. So we'll correct that. So if k is empty, and 0, otherwise calculate. Now it's corrected. Now we continue with the denominator, which has two parts, factorial k and factorial n minus 2k. So we start with the first part. So all over the quantity, factorial k times factorial, the second part is n minus 2k, n minus 2 times k. So, next, here we have the trend line polynomial. We have the regressions and the trend line. So we'll calculate these regression coefficients using Linus. To do that, we have to complete the 1 comma x matrix, which is equal to RA formula of the x values raised to the power 0 to 10. Now that we have the 1 comma x matrix, we can use Linus. So this is Linus to calculate the coefficients. So data y and data x. So here you have the coefficients, and we'll verify these coefficients against our polynomial here. So we start with n equals 0. At n equals 0, the Hermite polynomial equals 1. So that's 1, and it's 1 here. At n equals 1, our Hermite polynomial now is equal to 2x. That's 2x. At n equals 2, Hermite polynomial is equal to minus 2 plus 4x squared minus 2 plus 4x squared. At n equals 3, our Hermite polynomial Hn is minus 12x plus 8x cubed minus 12x plus 8x cubed. N equals 4. Hermite polynomial is equal to 12, that's 12, minus 48x squared minus 48x squared, 16x to the fourth. N equals 5. Hermite polynomial Hn is 120x, that's 120x, minus 160x cubed, 160x cubed, plus 32x to the fifth. N equals 6. Hermite polynomial equals minus 120 plus 720x squared minus 480x to the fourth plus 64x to the sixth. At n equals 7, Hermite polynomial is equal to minus 1680x, that's 1 minus 1680 x squared, or x, plus 3360 x cubed minus 1344 x to the fifth plus 128 x to the seventh. At n equals 8. N equals 8 is 1680 minus 13,440 x squared plus 13,440 x to the fourth minus 3,584 x to the sixth plus 256 x to the x to the 8. At n equals 9. At n equals 9 is 30,240x minus 80,640 x cubed plus 48,384 x to the fifth minus 9,216 x to the seventh plus 512 x to the ninth. N equals 10. Our polynomial is 30,240 x to the 30,240 plus 30,000 302,400 x squared minus 403,200 x to the fourth plus 161,280 x to the sixth minus 23,040 x to the eighth plus 1,024 x to the tenth. This completes the use of Taylor-Maclaurin series sum and Linus polynomial regression to generate the trend line of the physicist Hermite polynomials.